Iban Berganzo. He's from the Catalan Institute of Classical Archaeology, one of the partners of Master's project, and he will be talking to us about machine learning. Because as you could see from the presentations up until now, extracting sites manually from these maps can be both time-consuming, and people have different methods and way of finding features. So he's going to talk to us about how automatically these things can be done. Iban, I'm sorry for the delay. As I told you, you can use an extra 5 or a few minutes after, and we can adjust in the end. The floor is yours. So if you can share your screen.
Just let me.
Thanks very much, Iban.
Okay.
Yes, we can see your screen now.
And do you hear me?
Yes.
Perfect. Now full screen?
Yes, it is full screen. Thanks.
Okay, perfect. Okay. So, okay. Okay, so my name is Iban Berganzo. I am PhD researcher from the Classical Archaeological Catalan Institute, and I will introduce you to machine learning and how to use it in on historical maps. I will talk about the artificial intelligence, machine learning, its algorithms, how to use it in archaeology, and about how to detect on historical maps. Okay, so the first question is, what is the artificial intelligence? When we talk about it, we have to go to 1956, where it's the first time that this name was coined. And when we are thinking about, we think maybe that is more like science fiction one, no? As you see, this intelligent robot, but this artificial intelligence is called general. It's not the common one. It's not the one that we have nowadays. This is called weak. And what's the difference? The weak one is the real one, because thanks to machine learning, we arrived to make automatization and speed in our algorithms to have something similar to artificial intelligence. But not only thanks to the machine learning, also thanks to the electronics, such as graphic cards, GPUs, and so on. And the alignments that the highlights that we achieve are in automatic speech recognition, natural language processing, and in computer vision. The last one is one of the most interesting for us because it's the one that is more useful in archaeology. So, is it the machine learning the thing that we were thinking on, this intelligent robot, or maybe it's more like an algorithm that learns from our data sets? I think the question is more for philosophers, and we can continue knowing at least how to work with machine learning. So how do the machines learn? This is our data set. For example, all this data of the maps that we are talking today about. And the first thing we have to question about is with what language we will make to the machine learn. This is the program languages that we are common using it. The first one is Python, the second one is R, MATLAB, and Lisp. But we also have to take into account the modules, the libraries that we have to use to program in machine learning. This is TensorFlow, scikit-learn, Keras, OpenCV, NumPy, Matplotlib, and Pandas. And at the end, where we can program it and use it. we can use a Colab environment that use Jupyter Notebooks to program our algorithms of machine learning. So let's go. We will make to learn a machine. So what have to do and what have to do? We have to divide our dataset in 3 types of dataset. The first one is the training data. That must be the 50% of the whole data. And then the rest, in a 25%, is data to validate and test our algorithm, our training algorithm. So here you see that we take our training data and we have a model, a machine learning model that is an algorithm. Now we train our model with this training data, and we at the end have an error less than 0.05. We call it loss, but it is an error. If we have an error less than this, it's a good error, so we can continue with our algorithm and evaluate it. How we do evaluate? With the validation data. We pass the validation data to the training algorithm, and we will have some false positive and some false negatives. So if we score it and the score is low, we have to retrain our algorithm again. How we do that? Well, maybe adding more training data, the augmentation techniques, and changing models parameters. And then again, we train with these new techniques, and we again have an error less than 0.05. Then we evaluate the training model again, and now the score is higher. So now that is high, we can make the second evaluation. Now, not with validation data, we use the test data. And again, if the score is high, we can use our training and validating model to detect other data that we know, new maps, and that we don't use in the training step. And after detecting it, we will make prediction classification with a lot of accuracy. So which types of machine learning algorithms are now using in this field? The four most used ones are the linear regression, random forest, clustering, and deep learning. The first one, linear regression, is about correlation between different data. It's a supervised algorithm. We know the outputs for our inputs in the training data set, and we make predictions for new input data. So we will see a real case. It's about the diffusion of Gravettian technocomplex in Europe. And the hypothesis of this case is that one of these 3 sites may be the origin of the Gravettian. So the people who make this paper take off the data of the distance between the sites from these original sites and the appearance of the Gravettian in these sites. After training the algorithm, they obtain this line that is a correlation, a comparison between the distance from this original site and the data of the Gravettian in these sites. As you see, the R value, that is the correlation value, is a little bit low, it's 35%. This another one is from the second site, the Hessens cluster, and has a better correlation number. And this last one has again a lower correlation number. So which one is more likely to be the origin of the Gravettian in Europe? The Hessens cluster site, because its correlation number is bigger. So after doing this, now we can say, I found a new site that is an X kilometer from the original one. And using this algorithm, I can predict which is the data of the Gravettian in this site. This kind of techniques, low cost, and for example, we can know to do the radiocarbon analysis, because with only this algorithm, we have more or less the data of the gravity in this site. The second algorithm is the random forest. What's about? It's about decision trees. These are questions that we make about the features of our dataset. It's again a supervised algorithm. We know the outputs for our inputs in the training dataset, and we make predictions for new ones. A real case is a paper that will be published more maybe this week because it's accepted, and it's about detecting tumuli and whenever you want, but here is applied in the northwest of Iberia. The hypothesis of using the random forest is that we want to classify the soil into areas suited or unsuited for the presence of tumuli. And we use for dataset more or less 4,000 sampling points for Sentinel-2 bands. And here, as you can see, we have 1, 2, 3 the points that its features are the class if it's suited or not for tumuli, and the bands, the values that this point has in these bands. So this is our features for our points, and we make, or the algorithm made a decision tree question about these values, and then we obtain an image where we can see the places that are suited for presence, the black ones, and in red, the unsuited. So now we can search better the tumuli in the suited areas. Another algorithm is the clustering one. The idea of this algorithm is to group dataset objects according to their similar features. Why is that? Because it's an unsupervised algorithm. Here we have not the outputs, so we can compare with the desired ones, the prediction that we made. But the algorithm look for patterns in the input data, and then finding these patterns, it can classify the dataset objects into different clusters. To see it better, we will see the real case, that is the application of clustering techniques to group archaeological artifacts. And the hypothesis is we can restore ceramic amphoras and glass vessels from fragments. And the dataset that they use is the chemical elements of these fragments. So here again, we have 1, 2, 3 fragments that we don't know which amphora correspond to, and we take the data. After using this clustering algorithm, the algorithm itself will separate in 3 classes all of these fragments. And now we have that in real, we have 3. I don't know how to appear this. It's about, sorry. Do you see a red line in the screen?
Yes, I think it's an annotated function.
Okay, sorry.
It's okay. It's gone now.
Sorry.
No worries.
Okay. Now we'll continue with the last one, that is deep learning. It's based on neural networks. And as you see here, this is the first neural network made by Frank Rosenblatt. That it's quite complicated, but the key of this algorithm is the feature extraction. What is that? I will show you an example. These are Greek columns, and as you know, the first one is Doric, Ionic, and Corinthian the last. The features of these columns are, for example, the base, the material, the decor, pollutes, and vegetation. This is the data that in the traditional machine learning algorithms we must seek, because this is the data that we pass to the algorithm. But now in deep learning, we just only use images like this picture as input data. And we don't say which are the features, because the algorithm will look for them by itself. And maybe you think these features were better, but the algorithm will decide that better are others. So to understand it a little bit more, the deep learning, we will explain 3 types of algorithms that they are using the learning. The first one is multi-layer perceptron. But what is a perceptron? To answer this question, first we have to answer what is a neuron. A neuron, that is a perceptron, is a combination of the input entrance of the input data that, after applying a multiplication of weights that are numbers, we obtain an output. If we translate this neuron to a neural network, we will see that the neurons will be connected one with the others. And if we make a training, for example, the information will go from the input layer to the other layers, like in the image. And then when it arrives at the end, as we talked before, the error is calculated with a loss function and will go again backwards, changing the weights value. Because in the next iteration, the weights will be more correct than in the previous one. And iteration after iteration, we will obtain the good results with low error. To see this better, we will see an example that I have here. It's made by Google. And as you see here, we have a neural network. Our training data is are points. Are points like these ones that are blue or orange if they are in one position or in other. Here we have the X and Y position in this table, and we will train the algorithm. And you will see in the background of the image how the algorithm fits to the points. As you see here, we have the loss that now is 0.4. And here at the top, we are seeing how the epochs, that are the iterations, are going on. And as you see, the background, that is the algorithm really, is fitting with the orange in the orange points and with the blue in the blue points. And as you see now, the error is 0.1 or 0.04. So now we can stop it. And here we have the algorithm trained. So now if we use another new data, another points that we don't know its class, if they are orange or blue, the algorithm itself will say if they are orange or blue because it's trained. So this is how a neural network works. And the multi-layer perceptron. The next algorithm is the convolutional neural network. What is the difference between the convolutional one and the multi-layer perceptron? The only difference is that we are at the beginning a convolutional layer. This layer will allow us to detect local patterns versus the global ones. And how does the convolution works? As you see here, we have 3 images. The first one is our input data, that is a 7, and the convolution looks for the local pattern, the border from objects, or the more significant information. And then we make a group of this pixel to use the same important information, but in less size. And then this pooling is the one that will go through the neural network, as we see in the previous example. Two types of convolutional neural networks are, first one, the object detection. Why? Because we can find the local pattern, we can search inside the image for the object. For example, here we have an image where there are 3 tumuli that are the white circles. If we use our trained and validated model to detect these tumuli, we will obtain their position in the images. And the algorithm that we use to make these convolutional neural networks for object detection are YOLO, faster RCNN, and efficient depth. This is the newest one and the most efficient. And the other type is not only to detect the object, is to segmentate it. Why? Because if we are interested in their shape, like in this image, we have ceramic potsherds, and we want to know not only where they are, we want to know their shape. So after applying this algorithm, we will, as you see in the color potsherds, not only where they are, we want to learn its shape. And the algorithm that we use to learn this is the mask RCNN algorithm. And the last type of algorithm in the learning is the recurrent neural network. This is quite different because it uses sequential data, because it has the dimension of time. It's based on recurrent neurons, that is the same neuron that we see before, but with a feedback loop that it uses its entrance, but also the previous ones. So now we can decide whether the next prediction because we know all the previous input data. And the backpropagation is a little bit more complex, the way to update the weights. A real case is the Beethoven X. That is a work that appears the last week, where they finished the Beethoven's Unfinished Symphony number 10. For the dataset, they use all the Beethoven's music sheets. And what they use is only the beginning of this symphony to finish all of it. As you see, the music is sequential. It's important, the previous notes, to predict the next ones, not only the first before one. So to finish it, we can say, after knowing what is learning, what is machine learning, how to detect archaeological feature on historical maps. As we see before in the previous speaker says, this is a mound in a map, and we want to detect them. So first of all, as we see, here is an image, and the mound is in a position that not correspond with whole the image. So we need to feature extraction. That means deep learning. We need to find local patterns. That means convolutional network. And as we are interested in their shape, we need to make segmentation algorithm. So after all of this, which is the algorithm that we want to use for finding mounds in historical maps? Mask RCNN algorithm. So this is the bibliography that I have used. And thank you very much for your attention, and I will be answering your questions. Here you have my email, the Twitter accounts, and that's it. Thanks.
Many thanks, Ivan, for this very informative presentation. There've been a lot of information here, but we're happy that this presentation is, all the workshop is recorded, so you can have access to the link and you can follow on your pace. Now, if you have any questions, now it's the time to ask. I see that we already have one question from Pamela. Would you like to unmute yourself and read out loud your question, Pamela, to Iban?
Thank you, Zade. What I was asking, one of the methods, I think the first one that Iban has talked about is the use of linear regression for detection of archaeological sites. So my question was, given that archaeological sites don't necessarily depend on, ecological patterns or physiological sort of formations, maybe they do, I don't know, but I'm just thinking in terms of they're more of cultural and heritage kind of factors that lead to their being established in certain places. So how effective are the linear regression methods, which essentially rely on physical explanatory factors, like you want to list say they have to be close to a river, or they are located in soils of a certain type, and things like that, which may not necessarily be where archaeological sites are detected. In that case, how effective is linear regression, and especially when now they establish a correlation of say 0.5 or 0.6 or whatever it is, that this is, it essentially is like causality, you're trying to establish a cause for that archaeological site being located in a certain place, and yet you have a lot of other factors that are not physical or physiological or ecological that determine the location of archaeological sites. And in that case, then isn't it wouldn't a lot of post-processing be required, field work for verification and so on? Thanks.
Okay, thank you very much for the question. Yes, as you said, it's important to have a lot of data, because the algorithm, in this case the regression one, will search for correlations. If there are no correlation in the whole data you pass, the algorithm will say that the correlation number is very low. So this is not a good algorithm to use for this data if you don't have a high score. But as you say, you can use a lot of type of properties or parameters to try to search for this correlation. And at the end, when you finish with the detection, of course you can go to the field and check if it's correct, because this is another testing, that you can make to verify your algorithm.
Yeah, I just wanted to add that we are not using regression algorithms. We are using classification algorithms, because we are not predicting, but classifying our input data into sites or not sites. And we are using regression for other stuff, but we are not talking about it today. And yeah, as Ivan says, it's pretty clear that sites have a lot of different characteristics. And our approach to site detection now is to use as many of these characteristics as possible, not just their shape. I mean, the paper Ivan was talking about, this hybrid machine learning we have developed, is using multispectral, but also radar, is using also the shape of the site. So what we are trying to achieve, it's a definition of sites using as many characteristics as possible. And it's working pretty well. We don't use linear classification methods because they are too simplistic. They really don't work. I mean, you cannot classify. It's very difficult to differentiate sites from non-sites with a linear classifier, because it's data, I mean, the definition of a site is usually much more complex and wouldn't fit in a linear model. Okay, so yeah.
Thank you so much.
Thank you very much. So I couldn't see another question in the chat. If you have more questions, please you can email to us and we're happy to answer them. And if you have, I think we have time to answer another question. So if you maybe raise your hand, we can answer another question to Iban. Kezola, is that a new hand or is this from your question before? I see your hand is up.
It's a new hand.
Yes, I'm sorry, please go ahead.
Okay, thank you very much, Ivan. I'll go quick with my question. I'm trying to use deep learning with PyTorch, but then one of the issues, problems I have is that I first have to label the data on the satellite images. And then after I label, then I'll try to run the verification and all that. But then now I'm interested in combining historical maps with satellite imagery. Is there a possible way I can use those, train the data, and then somehow use it for example, if I'm trying to recognize new sites, train that data to recognize new sites on either historical maps or a combination of historical maps with satellite images? I don't know how you advise on that.
Yes, as you said, you can use whenever the input data you want, historical maps, or you can add more layers. The much bigger problem that you can find with this is that maybe the computational cost is a little bit higher. So it depends on your resources. As I said, you can use a Colab environment to train your algorithms and then to detect. But you have to take into account that it's a free resource, but it's not, I think you can work with it 12 continuous hours. So you can try it, but take into account that you need a good GPU and good other resources.
Thank you very much.
Thanks very much, Ivan. So now we came to the end of this 4 and some hours workshop, and I want to thank you all again for joining us. I want to thank the speakers and also thank you to my colleagues, Rebecca Roberts and Chris Matthews, who's been, and also Faye, and they've all been helping with answering questions and admitting people. Thank you all. So with today's workshop, our aim was to provide an overall understanding of historical maps. We tried to cover many different, both how to use these maps or what are the methods to use to analyze this map. And also we went to some technical parts of georeferencing using Quantum GIS, and also the machine learning part to how to better understand the past landscape and identify and detect possible archaeological sites. In order to facilitate this knowledge sharing, we thought it would be very useful to make quick or short guidelines on how to better understand these maps, what are the information that you find on the maps, where are the repositories, and what are the different iconographies on each maps. We've developed one for MASA, and the one for MESAM is under development, and I will share both the links with you. But I want to share the link for the one that we have for MASA, and I lost the chat. I'm trying to find where is I minimized that. Okay. I'm gonna add the link, or maybe if Junaid, I think Junaid has a link to the drive, so we can share the link with you. And I can quickly share my screen here. So this is mainly how it looks like. So it's a very brief and simple overview of the maps, and this one is specifically for the Survey of India maps. And what are the iconographies about the archaeology, different types of mounds, and any different heritage that you can find information on the maps. Where are the repositories, and mainly the repositories that we have in the UK, they are listed here. But we're gonna provide a link to the a live working document that you can also use that to add any repositories that you know in different part of the world, so we can build on this documents. How to read and understand the maps. This was part of also Junaid and Afifa and Jack's presentation as well. And what are the information that are available on the map, with a very brief section at the end with the extra sources and extra readings. Yes, now I want to just run the poll. This is very strange. Okay, so I can see it here. So there are the 2 questions that we asked you at the beginning of the poll. So if you can ask those questions, and also there are a few extra questions to understand better your needs or your preference for any future workshops and trainings that we're going to hold in the future. So if you can take a time before you leave to answer this poll, it will be very helpful for us. And thank you again. When you're done with the poll, you can leave. But if you can, I think you should be able to see the poll now. And thank you all.